so we'll get started. I'll try to do this at the beginning of every class. Sometimes it's just sort of, we're coming from everywhere. The other thing is I've got a camera up here. So like I said last week, you will occasionally maybe miss class, either because of illness or just because you can't be bothered. That second one really needs to be very infrequent. Like I said, I've got some stuff that we do in class that will E for points. So you should come to class when you can. I have no idea how well this will work. I had a system from the IT folks during the year we were teaching half and half. I don't know if any of you were here. You were here for that, right? Half populated classroom? No? There was a year there where like this class, we would only be able to put 18 people in it or something, and we had to rotate through. So I was recording everything, and I had a little system. And I realized, like, I really don't want you in class if you think you're sick. But telling you that and then just being like, here's the textbook, go figure it out, is not completely fine either. So this probably is, I hope this is not as good as coming to class. I'll see if like 5 of you show up on Wednesday, I'll know I recorded it well. But anyway, there should be, I'll make this available to everybody in class, and it should maybe help you even if you're here to go back. So today we're going to be looking at, we're going to start new material out of chapter 16, which is dienes, and out of chapter 17, which is aromaticity. And so if you talk to your friends in other classes, I think they're starting in chapter 12 and 13. They're just kind of going in linear order. Most of you in Orgo 1 finished with alkene chemistry. All right? Dienes follow alkene chemistry, aromaticity follows dienes really naturally for me, so that's where I like to start. We will go back and do 12 and 13. By the end of the semester, you'll pretty much have done all the chapters everybody's done. So, okay. Let me stop talking about business. And I put this reaction up the other day. Sort of a similar reaction. Go ahead and predict a product for that. If you're at home, actually predict a product for that. So this is an electrophilic addition to an alkene. I think it's chapter 8. HBr is an acid, a bronzed acid. The HBr bond is polarized. The bromine's quite a bit more electronegative than the H. So the 2 electrons shared between the H and the Br are pulled more toward the Br. Okay, so the pi electrons are relatively reactive. We're going to talk more about why that is today. And so your mechanism, your pi electrons are just going to be the nucleophile or the base. They're going to grab the H. And the 2 electrons in the HBr bond are going to go on the bromine. And that's going to get us an intermediate. This is not the final product. All right, get a carbocation. I'm only drawing the H that was grabbed that came from the HBr, right? There's a lot of other H's on there. You're going to see me do this periodically over the semester. I'll draw like 1 H in a molecule. And I'm not saying that's the only H. I'm just saying this is the H that's doing some chemistry and moving around and acting funny. So we're going to look at it. All right, and then from there, you've got a tertiary carbocation. Tertiary carbocation rather than, right, the other possibility would have been to put the proton here and make a primary cation. And this just goes, right, we can either make a tertiary carbocation or we can make a primary carbocation. The tertiary is a lot more stable. There's not really any steric reason we can't make the tertiary rather than the primary, in fact the opposite. And so we don't see this at all, right? You don't see this cation at all. No products that come out of that cation. So I'm saying the tertiary carbocation is more stable than the primary. I am not saying the tertiary carbocation is stable. I'm saying it's more stable. Okay, so this is not going to be your final product. Almost never, really, for introductory organic chemistry, you can just take this as a given. A carbocation is not ever going to be your final product. We've got a bromide ion in here. It's a weak nucleophile. Right? So this is a weak nucleophile. The carbocation, though, is a strong electrophile. Again, general rules. These are general rules. This isn't like, a well-established. It's not like gravity, okay? So general rules sometimes fail. But if you have a weak nucleophile, it's going to need, or if you have a weak reagent, it's going to need to be paired with a strong reagent. Right? If you have a weak base and a weak acid, those aren't going to do anything. If you have a strong acid and a strong base, those are going to react like crazy. It's a bad idea to put them together. Typically, we try to set up here's a fairly weak reagent. We're going to drive the reaction with a stronger reagent. Sometimes that's an external force. You guys have seen reactions at this point. We're mixing stuff together. You don't, even over here, the alkene is a weak base, a weak nucleophile. HBr is a strong acid. Right? So you've got to have something in there reactive enough to go forward. This curved arrow just says the bromide ion uses 2 electrons to make a bond to the carbon. And we add HBr across the carbon-carbon double bond. Okay, good. And if you want to look at molecular orbitals for this, if we look at this alkene from the side, I talked about this a bit in class the other day, right? We get this pi bond that's made up of 2 p orbitals overlapping, kind of above and below. You've got a sigma bond. The stronger bond that's holding these 2 carbons together is the sigma bond. That bond's 2 shared orbitals in a molecular orbital made up by 2 sp2 atomic orbitals overlapping. The pi bond, and that's what reacts, right? Because this sigma bond stays in place. That sigma bond doesn't go anywhere through this reaction. But the pi bond breaks. The pi bond is weaker. The overlap between these 2 p orbitals is less complete, right? The 2 cylindrically shaped sp2 orbitals can get in there and really overlap well. The p orbitals are sort of sliding together. There's a little steric propulsion. It locks the pi bond locks this in place. There's no rotation around this carbon-carbon bond. So it's more ordered, so entropy is not as favorable. Anyway, that pi bond, we say it's more reactive. The electrons in the pi orbital are higher in energy, and so they're the most reactive. All right, anything else I want to say about that? All right, so let's do this reaction then. And I'm going to draw it a little different. I'm drawing HBr above the reaction arrow. It's the same thing, right? Anything written above or below the reaction arrow, it's just add it all in there together. This is a diene now. Before you start predicting the reaction, let me talk about, this is a conjugated diene. All right. The 2 alkenes here are, we say that they're conjugated, and the way you know this is you have a pi bond, a sigma bond, and a pi bond. So conjugated dienes are 2 dienes separated by a single sigma bond. So not conjugated two double bonds in that blue structure are not conjugated. The two pi bonds are separated by two sigma bonds. Same thing. Those two double bonds are separated by multiple sigma bonds, so not conjugated. All right, so we're going to take this conjugated diene, we're going to try to come up with the product. So go ahead and do that. I'll give you a couple of minutes. Same thing goes for you guys at home. Draw me the product or products of that reaction. All right, so hope you got a product there. Wonder if I've, yeah, these poor folks can't read all that. All right, so I meant to mention this. You guys have all heard this. Markovnikov's rule, cool Russian name. Markovnikov stated that when he added HX, X could be Cl, Br, I, OH. When he did that, X always went on the more substituted carbon of the alkene. Right? So in this alkene, this carbon that I'm pointing at is more substituted. So again, if you're forgotten, in organic chemistry, we refer to a substituent really as anything that's not a hydrogen. Think about how we draw line structures, right? We don't draw any H's. We just sort of assume there are H's there. The carbon's going to have 4 bonds. If I don't show 4 bonds, the bonds not shown are H. So a substituent is anything we put in place of an H. So a substituent is something you're going to have to draw. A chlorine, a methyl, a phenyl, carboxylic acid, whatever. So this carbon's got 2 methyls on it. It's disubstituted. This carbon has no methyls, no substituents on it. So it's not substituted. So the more substituted carbon gets the Br. All right, so Markovnikov's rule was purely observation. Like these folks in the 19th century were really, like, there was no chemistry class, which might sound good to you. What there was hours and hours of lab. If you were a chemistry student, you went into some dank lab and you just spent all day adding one thing to another. Occasionally it turned a color, occasionally it did nothing, occasionally it made a smell, occasionally it blew your fingers off, and you wrote it all up, and someday hopefully we make sense of it. But we haven't. So you get to sit through class instead of blowing your fingers off. So he just observed this. And what we would say now is that if a reaction goes through a carbocation, so if you're drawing a mechanism and you write a carbocation, you better be going through the most stable possible carbocation, right? You guys might remember that carbocations can rearrange, right? And that's, if you have enough energy to make a carbocation, which is a pretty reactive intermediate, you have enough energy for that thing to start rearranging. Okay, so I hope, if we look down here, we've got an alkene. Let's just, simplest thing. Do the simplest thing first, right? We've got two alkenes. Let's add HBr across one of them. Okay, so bang, bang. We're going to get an intermediate here. Looks like this. And then Markovnikov's rule tells us, like that's, right, this is the more substituted of the two carbons, secondary versus primary, Br added there. Everybody draw something like that? Got something like that? Right, you can turn it over. You don't have to draw it exactly like it's drawn. Remember, these are symbols for the real molecule. The real molecule is a three-dimensional object that takes up space. You can take a picture of it from the front or the back or the side or 87.4 degrees above and to the left. You can take a picture of it from any perspective and draw it. So if you turn this around or flipped it over or all of that, that's fine. All right, so that is, in fact, one of the products of this reaction. As you might expect by the way I'm talking about it more, there are a couple of other products. Yeah, let's stop there. All right. How do we get that molecule? Have I? Yeah, okay. If you didn't, did anybody draw that molecule? All right, a few people, yeah.
Carbocation rearrangement.
So it's not exactly a rearrangement. It looks like a rearrangement. And I'm glad you said that because I want to talk about it from that perspective. So this cation, right? You could imagine. Yep, sorry.
I was going to say it's a resonance.
It's resonance, yeah. So you can imagine moving electrons here, right? So I'm going to redraw the cation. Draw that H in. So here's our cation. Now I can take the pi electrons. Take these pi electrons and I can move them there. Always count your carbons, get the right color with your marking. This is very entertaining for the folks at home watching my back. So those two cations are resonance structures of each other. So it's not quite a rearrangement. In a rearrangement, do all right, so if I have this primary carbocation, sorry if you were down on your notes, I just redrew just like a random primary cation that came out of nowhere, all right, except my head. This has nothing to do with the reaction we've just been doing. But if we have a primary carbocation like that, this hydrogen can migrate over to there, and we get a secondary cation. Right? Those are not resonance structures of each other. Those are two separate, distinct molecules. Neither are stable, but one is quite a bit more stable than the other one. This primary carbocation actually it's really hard to make. Like, I don't know who you had for Orgo 1. Did anybody in here have me for Orgo 1? Cool. I thought there was one, but I couldn't remember. All right. So I might have gone into this more than you appreciated at the time, because you're going to love it now, right? Making a primary carbocations are so unstable, they really don't exist. If you see a reaction that appears to go through them, there's some really complex stuff going on. Secondary carbocations are stable enough you can make them. Tertiary carbocations, resonance stabilized carbocations, definitely you can make those. Primary are kind of hard. So this reaction actually goes to the right part. If you even get a hint of that primary carbocation that I've drawn there, you're going to have the second. You're going to see products derived from the secondary cation. All right, up here on this one, it's not the same story. This looks like a primary versus a secondary. Okay, but you've got that double bond next to it, and those pi electrons are interacting with the vacant p orbital on the carbon. All right, so you see how I've drawn this molecular orbital. Have a shot at drawing the molecular orbital for this resonance stabilized carbocation. Yeah.
Does that first product have stereochemistry?
Yeah. So before you start on that, this cation obviously, or that bromide obviously, is not in the same plane as the other two carbons. All right, it's racemic, and so I'm not going to show a wedge. I'm not going to always draw both of them. If it's a chiral center and I don't show what it is, it's racemic. Right? Half of the bromide's on top, half is behind the board, and you can think about it from this step, right? The carbocation is trigonal planar. Half of the p orbital is sticking out towards you, half is going away. So the bromide can either make the bond from this side or it can make it from the other side. And there's nothing to make it go one way or the other. All right, give that MO a shot there. How are we doing? I'm a lousy artist, by the way. All right. Keep looking down and working on it, but if you've given up or just are tired of trying, I've drawn the pi bond there. All right, so again, this is just a pi bond is just two p orbitals on adjacent carbons. So two carbons sigma bonded to each other that have a p orbital. Those p orbitals overlap and give you a pi bond. All right, so this carbon is sp2 hybridized, that carbon is sp2 hybridized. P orbitals overlap. I haven't shown it that way. Well, it turns out this positive carbon, throw the charge in there. All right, that positive carbon also has a p orbital, and so it can overlap. And this is really what we're saying with this curved arrow where we say resonance. We're saying these two pi electrons can also be here. And in fact, it's not a rearrangement. And seriously, this is the way you're going to think about it. This is an easy way to think about it. It's the way I thought about it for a long time. Resonance is a very, very simple idea, and it's an idea that is also really hard to put in your head. These two electrons are not just there. They are also not just there. Right? Those two electrons, we really have trouble drawing the structure for those two electrons. The real structure looks something like this. This is the way we usually would draw it. Right? Sort of a dashed line there, the electrons spread over all three carbons, and just all three carbons together are positively charged. The weird thing is we almost always end up putting this plus in the middle, and the carbon that's never going to get attacked is the middle carbon. Right? Most of the positive charge exists on the two end carbons. Right? Because if you look at the two resonance structures, right, the real structure is a weighted average of these two. So it looks a little more like the secondary cation, because the secondary cation is more stable. But not like 99 to 1. It looks a good bit like that. Okay, so right, if a nucleophile hits here, it can push these electrons there and neutralize the plus. If a nucleophile hits here, it neutralizes the plus. Nucleophile hitting that middle carbon never neutralizes the charge. Okay, you can't push electrons and neutralize that charge. All right, so when you have this is called an allylic cation. This is nomenclature, which I've been an organic chemist for over 30 years, so I'm decent at nomenclature, but that's the only reason why. Pretty lousy at teaching it. So I'll make reference to some nomenclature sometimes. You should look at some nomenclature. You'll see it. You might see it on the MCAT. You might see it on the. Anyway, we'll talk about it. I promise to do a little bit of nomenclature. But so a couple of nomenclature bits. A double bond like that as a substituent is known as a vinyl. All right, so if I have a carbon-carbon double bond with nothing else on it, that's a substituent. If I'm referring to that as a substituent, it's called a vinyl group. V-I-N-Y-L. Where else have you heard vinyl? Records. The reason is one of the polymers, one of the principal components of records is a polyvinyl polymer. And that's where this vinyl came first, and it went into the record. Any position, so like this methyl here, a position that is next to a double bond, that's called an allylic position. So if there were a bromide there, it would be an allylic bromide. All right, you're going to have to get the rest of it on the next video.